This lesson will look at geometric probability. You'll learn how to solve problems involving geometric probability and solve problems involving sectors and segments of circles. How can geometric probability help you to win a game of darts? To win at darts, you have to throw a dart at either the center or part of the dartboard that earns the most points. In games, probability can sometimes be used to determine the chances of winning. Probability that involves a geometric measure, such as length or area, is called geometric probability. If a point in region A is chosen at random, then the probability, P of B, that the point is in region B, which is in the interior of region A, is the area of region B divided by the area of region A. This fits nicely with our basic definition of probability that is favorable over a total number of outcomes. When determining geometric probability with targets, we assume that the object lands within the target area, and it is equally likely that the object land anywhere in the region. A game board consists of a circle inscribed in a square. What is the chance that a dart thrown at the board will land in the shaded area? Well, we want to know the total area would be the area of the rectangle, which happens to be a square. So it's 12 by 12. So 12 by 12 is 144. And the area of the circle is pi r squared. If our diameter is 12, the radius would be 6. 12 divided by 2. So pi times 6 squared would be 36 pi exactly. So when we go to do probability, probability is favorable over total. So we want it to be in the shaded area, which is inside the square but not inside the circle. So we need to take 144 minus 36 pi out of our total is 144. And that doesn't look like much of anything. We need to type it in the calculator to get an answer that makes sense. And I get 0.215, which would be 21.5% of the time. And they just left it as a decimal, so we will too. Sometimes you need to know the area of a sector of a circle in order to find geometric probability. A sector of a circle is a region of a circle bounded by a central angle and its intercepted arc. So it's like a pizza pie or pizza. This should look very familiar. Just like the arc length, we use circumference times the degrees we had over 360. If a sector of a circle has area A units, a central angle measuring n degrees, and a radius r units, then A equals n over 360 times pi r squared. So the number of degrees we have divided by 360 times the area of the whole circle. If you write nothing else in your notes, please write down the formulas. This formula we will be using. Okay, to find the area of the shaded sectors, first we're going to have to find the radius. So we need to take the diameter divided by 2, so 9 inches. And you probably wouldn't show this step either. We're going to add and get our total angle that is shaded. So 45 degrees plus 35 degrees would be 80 degrees. So plugging into the formula, we have 80 over 360 times pi times 9 squared. We can simplify that and we get 18 pi, or probably be nice to round, be about 56.55 square inches to the nearest hundredth. Find the probability that a point chosen at random lies in the shaded region. Now you already have the area of the sectors was about 56.55. The area of the whole circle would be pi r squared, so 81 pi. And then we type that into the calculator to get an approximate answer. We get about 22 hundredths. We remember that probability of an event can be expressed as a decimal or a fraction. These numbers are also sometimes represented by a percent. This book at this point is leaving them as decimals, so we will too. Now, unfortunately, our next definition sounds an awful lot like sector. Now we need to look at a segment. The region of a circle bounded by an arc and a chord is called a segment of a circle. To find the area of the segment, subtract the area of the triangle formed by the radii and the chord from the area of the sector containing the segment. A regular hexagon is inscribed in a circle with diameter 12. Find the area of the shaded regions. Okay, so if our diameter is 12, we know that our radius is 6. And there are 6 sides to a hexagon, so 360 divided by 6 is going to give us 60 degrees for our central angle for each one of those. So we're going to have 60 over 360, which reduces nicely. Times pi times 6 squared, so that actually simplifies out really well, is going to be exactly 6 pi. Decimal, if you want it, would be 18.85. And that would be the area of one of the sectors. We're going to find one segment and multiply it by 3. So next we need to find the area of that triangle so we can subtract it out. Okay, because it's inscribed in a circle, if one radius is 6, they're all 6. And we said 360 divided by 6 gives us a central angle of 60. When we draw in this altitude, which is our apothem, it's going to cut that 60 in half, so it gives us 30, and this is 90, so then this is 60. We have our friend the 30, 60, 90 triangle. So using that reference triangle again, our sides are 1, 2 square root of 3 times our ends. And the part they gave us was the hypotenuse. So we know 2n equals 6, so n must equal 3. Oh, they've got that labeled already. And that means our altitude must be, the side adjacent to 30 would be 3 square root of 3. And we know area of a triangle is 1/2 base times height. The whole base of this triangle is 6. The altitude we found was 3 square root of 3. And when we type that in, it would be exactly 9 square root of 3, which as a decimal is about 15.6. So to find the area of one of these segments, we're going to take the area, the sector that we had is 18.85 minus the area of the triangle we just found is 15.6. And we're going to get 3.25, and we've already rounded. And then this, they wanted us to find the area of 3 of those. So I'll just multiply by 3, and we have 9.75. And they didn't give us a label, so square units. Okay, so same beginning, regular hexagon inscribed in a circle, diameter 12. Find the probability that the point chosen at random lies in the shaded regions. And we know probability is favorable over total, so the favorable we just found was the 9.75. The area of the whole circle would be pi r squared, so our radius was 6, so 36 pi, which dividing it out on the calculator, I get about 0.086, which we don't expect it to be very likely. It's not very much space. So as a percent, we could land in the blue section about 8.6% of the time. So wrapping it up, to find a geometric probability, divide the area of a part of a figure by the total area.